So if you ask me, air conditioning has been around for like 100 years. Airlines have been around for 100 years. So what exactly is new, right? So these things were getting along just fine till we computer scientists and our cousins, the electrical engineers, came across, and then we said, okay, we'll make all these systems smart by putting all the sensors in components and subcomponents of physical systems. Okay, so that is what we have been doing. Now, this commoditized sensing and scalable computing has given rise to a lot of possibilities. So we have a lot of data coming in from multiple different physical systems from the physical world, and we have this observational capacity. What we call as decision making is actually real-time decision making, right? Suppose an airline needs to make a decision to hold a departing flight for incoming passengers. I talk about this particular case study. It could also be for a LEED certified energy efficient building. You might want very good control of the HVAC system depending on the dynamics of today's weather condition, even though you would have some predetermined set points. Okay. So there are many possible such examples where you want to take a real-time operational decision. It's not a planning problem, just to distinguish from typical planning problems. These are operational decisions that we want to take in real time. And why do we want to take these decisions? We want to extract some business value out of it. Typically, it is to improve the efficiency of operations, right? For example, if I have a air conditioning system, I want to make sure its energy consumption footprint is as low as possible while maintaining user comfort. Okay, so that is an example of efficiency. You might want to improve the asset health. If I take the example of say a wind turbine, usually they are positioned in places which are naturally very harsh, right in the middle of the sea, or in the plains with a lot of wind, right? So there is like wear and tear of the blades of the wind turbine, depending on the shear forces acting on the wind turbine. And if it is possible for us through clever algorithms to improve the useful lifetime of a wind turbine, that would be a good example of improving the asset health, right? And finally, there is always this idea, if it is like a business to consumer kind of domain, for example, intelligent transportation is one domain. I might want to improve the user experience, right? As a passenger, if I'm taking a multimodal transportation system, I want to have like a seamless journey. Okay. Now, all of these things translate to business value, and that is what my colleagues in business keep telling us all the time. So there is significant motivation for us to look at this problem of decision making for the physical world. Okay. Now, what are the challenges in doing that, right? So now everybody sees that there is some value out of it. What are the challenges, typical challenges which happen? The first major challenge is the question of incentive, right? Let me, for example, take the case study of energy efficiency, right? Suppose you have like a way to deploy sensors for reducing the energy footprint of a building, or it could even be an entire campus. So the first question which people will ask is, what will you save for the investment I'm doing in terms of like sensing and the deployment of your clever algorithms for decision making, right? Will it still be compliant with all my business processes? Okay. And then there is a question of trust, right? So these are all systems which have been around for a very long time, and generally the attitude is, as long as it's working and it is not broken, let's not go and fix it, right? So let's take in, for example, even the TCS campus in Suruseri, right? It almost qualifies to be an MLA constituency, I think. So it's so huge, and we have like so many different chiller banks which power the centralized air conditioning of the entire campus. Okay. Now, I might say I will like sort of improve your efficiency, etc., etc. But on the day the customer comes, an important customer comes, I don't want the comfort to go for a task, even for a very small period of time, right? So that level of trust needs to be built in for the end user to accept such decision making. This is true in general, not necessarily for physical systems, but for physical systems, it is particularly so because the infrastructure is huge and legacy. Okay. Then there is the question of data. Okay, so physical systems, by their very nature, you have a lot of noise coming in. Even if you have like a huge quantity of data which is available for machine learning, the quality of data might be a problem, right? And if I look at large systems, like say, for example, an entire airline network, typically the data is in like multiple different silos, and these silos may not talk to each other, and so on, right? The other challenge in data is a brownfield system. If you are designing a new campus from start, you can deploy all the technologies that you have access to today. But then most of the systems are like brownfield systems, and therefore you need to take care of the transition from existing things to what is the art of the possible. Okay, so these are some limitations in terms of like the sensing part or the data collection. In terms of actuation, so you have collected the data, you have made some intelligent decision. Now that actuation sometimes is not under the control of the system integrator, or it might not be available or exposed for reasons of safety. So that is another challenge. Okay. Then there is the question of where the rubber meets the road. It's a question of implementation, right? So we want to solve problems at scale. So I'm not interested in problems which are like, say, I come up with the latest cool algorithm which I show on a small test bed, or like a simulated environment which is like, of very few problem instances, right? So we want scale, and usually it is like a system of interacting systems, right? And like I mentioned before, you want to make decisions in real time. So this is where the difference between your conventional algorithms and optimization sort of differs for physical systems. Then again, the standard questions of modularity and change management. Okay, so we sort of had a quick look at what are the typical challenges which we have faced in the industry when it comes to deploying decision-making intelligence for physical system. Now, how do we handle these challenges in practice, right? Um, what we have seen, at least this has been my experience, others could have different experiences on this. What we have seen is that you first start off with whatever data is available, right? Some data which comes from the real world, you take it as it is. Then you build a model for the decision making, right? And you demonstrate. So if the data is incomplete, you synthesize. If the data is like erroneous, you sort of fictitiously correct, whatnot, right? So this is just to show some potential business value from real world data on this model that you have built. Okay, then you sort of incrementally deploy in the real world. For example, if I were to do the energy portfolio of one entire retail customer, I might start with like a small POC in one particular location, customize my model for the weather conditions in that particular location, and show something tangible and valuable to the customer and build trust, right? And all of these things, it is always like in your typical software development, it is always like a sprints and you keep going forward in time. So today I will focus on some of the models that we have built for such decision making across like a bunch of domains. Some of these models we have been successful in deploying them in practice. Some of them are sort of still only at the lab level. So this is what I'm going to focus on today in terms of like the talk. It will be more on models for decision making. Okay. So anybody have a suggestion on who this is? Any guesses? Suggestions on the chat? Okay.
If I think you can add your comment in the Q&A. I see somebody raising the hand, but you cannot talk, unfortunately. So you can type your questions.
Okay, so let me just continue. Let me not interrupt the flow, right? I mean, this would have been good in a interactive live session. Okay, so this is George Box, a very famous British statistician, right? So he is, if you've worked in time series modeling, especially the seasonal ARIMA kind of modeling, You'd be familiar with the Box Jenkins methodology for identifying the order of a time series model, right? So this statement he made is this is something which has sort of resonated with me particularly very deeply. All your models are wrong in the sense that a model is only an abstraction of reality. Okay, so it is not reality itself. Okay, but some of them are useful. When it comes to physical systems, just like you have noise added for free, you also have physics added for free, which means the data that you are collecting from a physics system. So I have like a real world physical system, which I want to model. So what we do is you build a digital twin of this. I'll talk about how exactly we do this through some examples in the case studies, right? And this digital twin is like a high fidelity model of the physical system. And any real world data that comes in through your sensors, you add another pipe to it to your digital twin, right? So once you have this kind of like a in silico model of your physical system, I can use this to do many kinds of analysis, right? Usually, the first level of analysis is you don't need any big intelligent decision making, etc. You just allow the end user. It could be, for example, the facility manager of a building energy system. It could be the gate manager at an airport. So these are all people who are in the front line and they are actually managing the systems. All they want is the capability to see if I change some parameters, what would be the impact of that? So the so-called what if analysis. The other kind of analysis is if I want some particular end objective, what should I do in terms of my control knobs, right? So that is the kind of analysis that we do in a digital twin. And using this, you can either have like an automated or manual decision making. And this decision that you do would be pushed into a system of record. Okay. Now there are two things. You remember the challenges I was like talking about, the various questions of trust and scale. So this analysis, is what if analysis, we believe is the first step to build trust with the end user, right? So if they can see, at least for simple cases, that if they tweak these parameters, your model behaves like they expect, then they are likely to accept the any automated system recommendation that comes out of your intelligence. Okay, so that's the first one. The second point is when you are making the decision, it doesn't need to be like one particular technique that you use. It could be optimization, it could be ML, it could be RL, it could be combination of all of things, right? You want to aim for scale and speed even at the cost of optimality. Okay, so that's the point that I would like to mention here. Okay, so this is the structure. So any questions so far, or should I move along?
I didn't see any questions. Maybe we can continue.
Yeah, I'll continue. Okay, fine, good. So there are like this is how I'm going to structure the rest of the presentation, right? So I will talk about a physics-based modeling first. This is more to do with building energy management that I was talking about and wind energy. The next part of the talk would focus on transportation as a domain. Here we usually use some discrete event simulation model and combine that with a reinforcement learning agent. After doing these case studies, I would like to spend a few minutes talking about what is the future of such decision making in the presence of agentic AI, which is like, it's a tsunami out there and it is taking the world by storm. And I believe that it will also impact the way we do decisions in the physical world. Right? So, a few minutes I will talk about. Okay, so I think I have about 40 minutes left. So maybe I'll cover as much as possible. If you have questions, Krishna, please feel free to interrupt me at any point.
Yeah, sure, Arun.
Right. Yeah. So the HVAC control problem. Okay. Now here is a typical energy consumption. So the chart on the left, right? So the pie chart on the left, it's a fairly old chart, but it still holds, I think. If you look at the energy consumption of a typical facility, especially in developed economies, I mean, they are our main customers, unfortunately. You have about 50% of the energy consumption going in your heating, ventilation, and air conditioning. That's the so-called HVAC system. Okay. And what happens is that usually people want comfort, right? So they prioritize comfort. So if that facility actually requires X, right? What they would do is they would provision for the worst possible day of the peak summer season, and then design the HVAC system for that worst case condition, right? And when you look at the operational logs of HVAC systems, you will find that most of the time these HVACs are partly loaded. And like any mechanical engineering system, if a system is like part loaded, it will not be operating at peak efficiency. So you have a problem right there, right? So 50% of your energy is going for HVAC, your HVAC is part loaded, right? Can we do something better? Your typical building management system will try to do some kind of like a PID, that is like proportional, integrative, and differential. I vaguely recall that. So it'll do some kind of like a PID control, right? Which tries to maintain the comfort. It doesn't care too much about the energy consumed, right? So if we take a slightly more intelligent perspective, let us delegate the task of deciding the actual flow rate of the air handling units, the actual VFD speeds if required, etc., to the BMS controller. But I can operate at one level above the BMS controller and dynamically decide the set point. Now, what do I mean by dynamically decide the set point? Now, Chennai is a very hot and humid place, as all of you know. But today, if I know, for example, that the weather is going to be cool from some local forecast, can I dynamically adjust my set point in real time, right? Using a model of my building's energy footprint. Okay, so that's the big picture we are trying to get here. Now, this is usually not done, right? Seasonally, they will set the set point saying if it is the um, summer season in Chennai, make sure that the return air temperature is around 22 degrees, right? So that would be like some rule of thumb which they will follow, and there isn't much intelligence involved there. Okay. Now, for us to decide what is an optimal set point, I need a thermal model of the building, right? Now, this thermal model, what does it do? It takes the set point, which is sort of, it needs to output the set point. It takes the current humidity, ambient conditions, etc., and then it tells using an optimizer, it tells what should be the set point which the building management system should implement. Okay, so this is roughly the flow of the thing. Okay, now this, if you look at this box diagram, there is this thing called m of theta, which is an estimation of what is going to be the energy footprint. So this is where we will combine physics with machine learning, right? So everybody, I assume, is like familiar with the neural networks and so on. So I will not go into it, right? If I can augment a neural network with physics-based equations, then I have the best of both worlds. So I know that the data which comes from a heat load calculation will follow a physics-based, thermal model anyway, right? I mean, that's physics, right? So if I can incorporate that into my machine learning model, then I can do much better in terms of like the estimation of like the unknown quantities than pure data-driven machine learning models. Okay, so that's the hypothesis we had, and we sort of worked on it with some real-world data on a test bed. So I mean, there is some math here. I will probably skip that. The basic point is to get the uh, output of the heat load calculation, etc., which is your XT, what is the temperature evolution as a function of time. I just need to do a neural network forward pass. I don't need to solve a differential equation, which I would normally otherwise would have to do. Okay. What is the advantage of doing it, right? So here are like some charts, right, which give you an estimate of how good things are. So if you look at the temperature and the ambient temperature, then the achieved temperature is your TW, and then there is like a humidity. You will see that the physics-based model matches the ground truth exactly, almost exactly, right? The more interesting thing is, if I use a purely data-driven model, for example, I think in this case we used an LSTM, we probably experimented with something else too. but this is what we had in the paper, right? Sometimes the predictions can be sort of negative, right? Which doesn't make sense. Okay. But if I use a physics inspired model, you will see that the laws of physics are obeyed for free because I have already incorporated that into my machine learning model. Okay. So that's the advantage of combining ML and physics in this particular context. So in terms of energy consumption, we were able to improve the energy consumption, meaning we actually reduce the energy while ensuring comfort. And because this is like a ML forward pass, we could sort of achieve scale instead of solving like a governing differential equation. Now, this is a piece of work which we have managed to actually put it in practice. This is deployed at some TCS facilities. So we have like an energy management system for TCS, and this is also an offering from TCS for various customers. So there are a couple of papers which, if people are interested in, they can get more details about it. 2022 ACM builds us. There is a publication on physics aware control using ordinary pins. The second one was like last year, and this looked at using graph neural networks for the ML model. Okay, so let me go to the second problem, which is a problem in wind farm control, right? So here is the problem statement. So you have a wind farm, which is basically a collection of wind turbines, and there is a flow of wind which sort of comes. What happens today is that um, every turbine makes its own internal decisions as to how to react to that wind stream, right? If the wind is too low, for example, it will cut off the production. If the wind is too high, also for safety of the blades, it will sort of cut off the production, whatnot. So what we were interested in doing is, okay, the entire farm is going to be under the control of a single operator, and he is interested in the overall farm's energy output and the health of the overall farm, right? So these two things are typically conflicting objectives, because if I try to extract the maximum energy out of a wind turbine, I'm probably putting a lot of shearing stress on the wind blades, which will reduce my health of the turbine over a long period of time. Okay. So there is a trade-off between these two things. And what we were interested in doing is, if I know the weather and if I know the demand, which is basically what the grid allows me to produce at that point in time, how can I find out what is the optimum configuration of the wind farm at a farm level, right? So it is not an individual turbine level controller. Now, the one natural question which might come, right? Maybe that individual turbine level control is good enough, right? So what happens is that when one turbine sort of like tries to extract some energy from wind, it affects the downstream turbines. Okay. So maybe there is a joint decision of these three turbines taken together, which is better than each of these guys individually deciding for themselves, right? So that's the perspective that we took, and we were able to get some decent results out of it. I think this also went into uh, one of the offerings from TCS's IoT division. So we were able to get better performance in terms of both the energy output as well as your health of the turbine, characterized by the number of years remaining to failure. Right. So there is again another publication called Falcon Farm Level Control for Wind Turbines. It appears in the Renewable Energy Journal if somebody is interested. So, any questions on the physics-based models so far?
I didn't see any question, but I myself has one question, Arun.
Yeah, yeah, sure, sure. Go ahead.
Maybe some of the attendees also might have similar questions. So most of the times it looks like to me that these are distributed systems, right? Large scale distributed systems. And so only one kind of model building and deploying is sufficient in such settings, or we need multiple different types of models?
No, no, no. Multiple, absolutely great question, right? So it is not possible. So even this wind farm model, when you take this farm level model, right, centralized optimization will not scale. Okay. So in this case, we did exactly sort of, I mean, I didn't go into the details for lack of time. We had like distributed agents, right? It was more of like a some kind of multi-agent RL, each of which was like trying to optimize for one group of turbines. So some kind of hierarchy you need, and they sort of coordinate and make a final decision, right? So that is the usual approach that I completely agree with you. Yeah,
Mhm.
it is not.
And
It's not possible to scale.
and and uh, and
Okay.
the follow-up
Yeah.
question
Go
is
ahead.
that you need to how frequently do you need to fine-tune the models and so on?
That is a great question. So what we have seen is there are a lot of seasonality patterns. Okay.
Mhm.
So what usually works for one season doesn't work for another season. Right. So what we usually say is at least 2-3 years worth of data we need to do, and
Mhm.
we might need to do some high-level segmentation of the data first before we even do some specific model building, right? So, but that retraining part we try to do it at a preliminary data analysis part itself
Mhm.
instead of putting that retraining as part of the model building per se,
Mhm.
right?
Yeah, understood. Yeah.
Okay.
Thanks, Arun. Yeah, I think that answers.
Cool. So the next case study is on airline operations. Okay. So here is a example of decision making in airlines. Now, if you look at the on-time performance of airlines, that is a key performance business indicator for most airline companies, right? Usually 15 to 20% of flights are not on time, right? Which means that they have violated their takeoff time or landing time given in the schedule by more than some number of minutes, right? Different airlines, airports have different thresholds, but roughly 15-20% of flights are considered to be not on time. Okay. If you look at the breakup behind that, right? So if you have a breakup of the root cause for why these delays happen, you will find that most of the times it is because the incoming aircraft was late. You will also see these announcements, right? Late arrival of incoming aircraft. They will say that as if that it is not under the airline's control. But actually, that incoming aircraft being late also is possibly under the airline's control, right? So that is one reason. Second reason is your ground operations are not on time. Right? Something may not work. The fueling may not happen on time. The turnaround which happens on the ground may not be efficient. Right. So many things, many possibilities can happen. Okay. Um, the other two reasons are outside an airline's control. For example, if there is like some say missile testing, or if there is like an emergency situation, the Central Authority for the Airline Operations, DGCA in India, FAA in the US, these guys would take a call and say Eastern Air Corridor is closed, the air corridor along the Wheeler Island area is closed, and so on. Right? So these two things are perhaps outside an airline's control. Even weather, I would say these days you have like very good real-time prediction of the weather, right? But airlines usually tend to reactively, handle the situation rather than proactively plan because of exactly what Krishna was saying, right? It's a question of scale. There are too many things going on. Okay, so the key question that we are interested in answering here, a lot of this goes into a product in TCS called TCS Aviana. How can an airline handle delays to minimize the impact? Okay. So the first tackled in mind is the hold no hold decision making. What is the context? So suppose you are connecting. Suppose you are flying to the US. Usually what happens, there's a stop flight to your destination. You go to a hub airport, maybe Dubai, maybe Frankfurt, whatever, and then you go to the next flight that you take, which will take you to your final destination. Right. Now at the hub airport, you might want to make a decision to hold a departing flight. When is that possible? Suppose there are like say 20 passengers who are traveling from Chennai to say Austin or something, right? And if the departing flight from Chennai is delayed for some reason, right? I mean, there is always construction going on in the city. something happens in an arterial road. So if a lot of passengers are delayed in an incoming flight, should I hold the connecting outbound flight? So that is the hold no hold problem. It's fairly common in airline operations, right? So they know this problem for a very long time. Now, I mean, you can have some rules of thumb. That is what they normally do. Okay. Here is a example to sort of illustrate why this hold no hold decision making is sort of not easy, because it has lot of higher order impact. Okay. So suppose I have this flight, a lot of people are connecting from Singapore to Bangkok. I mean, this flight is going from Singapore to Bangkok and then onward to Hong Kong. Now, suppose I sort of hold a flight at Singapore for people going from Singapore to Bangkok. Then the flights which are following for that same aircraft will also get delayed. Okay. So there is a so-called aircraft or tail propagation of the delay. The other factor is, if I allow these late connecting passengers, maybe they have a further connection somewhere. So there could also be like a passenger propagation of a delay, right? So I might have like several holds and so on. So there is no simple way in which we can characterize all of these things in a series of rules which will work in all the conditions. Okay. So that is a problem. And the most important point is, my local decision that I take at one particular airport can have like a global impact, which means that your local value of the number of passengers that you save is not necessarily the same as the global value. Okay. So that is the problem that was sort of posed to us, and we tried tackling this from in a slightly different perspective. What we said was, okay, there is of course like this baseline approach, doing optimization. You can all the data, you optimize your branch and bound to come up with simple approximation. Now that out very clear, because that would be occurring on one day. For example, a leading airline in North America would probably run around 4,000 flights a day, right? About, I don't know, so many aircraft proportionately. Now that is the kind of scale which we are talking about in terms of like the decision making, and that is non-trivial to do in a okay.
Yeah, and we lost you again.
Sorry, I don't know. The Zoom keeps kicking me out. So I guess I was talking about this digital twin.
Yeah, and I'm sorry, you need to share again the slide deck.
Oh, sorry. I am sorry. Visible?
Yeah. No, slide deck is
Okay.
probably.
Okay.
I think I request you if you can start from this slide beginning.
Yeah. Sure, will do. Okay. So this hold no hold decision making, right? What we are trying to do here is we want to hold a outbound connecting flight for delayed incoming passengers, right? So I was just saying that there is no single rule-based approach to take all of these things into account, all of these higher order effects into account, and then come up with a decision. And centralized optimization is not really scalable. So we said, okay, can we do something in between? Can we learn a policy using reinforcement learning rather than actually you know, come up with a series of rules, right? Let's learn the rules rather than write it by hand. So that was the idea. So we proposed to build a airline network simulator, right? So that's what we did. That was our digital twin. Obviously, this was not like a live system, because airlines are like very wary of like putting things in a prod or dev environment, right? So they gave us offline data. They gave us data in terms of like the movement of aircraft and the movement of crew and the movement of passengers, right? Passengers, obviously, they gave us an anonymized manner, right? So we did this. We used all of this data and we built this network simulator. Okay, which this is the digital twin idea I was talking about. The core of it, I mean, this is like far simplified because it is not really a real-time environment. It is an offline model, but we validated it with the customer in terms of like some performance metrics that they would see from this model and what they saw in actual live operations, right? So that's what we did. Now, using this network simulator, we trained a reinforcement learning agent, right? So we had like a very hand-engineered state, probably not the best practice right now, but when we did it, then it was considered okay. So it was a very handcrafted state and handcrafted reward, which basically explores the trade-off between the local decision that you take for the hold no hold decision as in terms of like the global reward that you get from your uh, um, airline operations, right? So and we showed this to a leading airline, and some of it I think eventually went into their system as well in some form, right? So we were able to show a significant improvement in reducing the number of missed passengers, while the on-time performance did not dip too much, right? So essentially, the system somehow learned how to exploit those places where you can err on the side of holding a flight. The cost is like you add some additional delay, but the benefit is you save a lot of passengers and the associated customer satisfaction and the associated ticket value and so on, right? So we had a paper in AMAS 2021 in the main track, right? So that was the hold no hold decision making problem. And we had a follow-up paper in AMAS last year, 2024, which sort of generalizes this problem, right? So hold is like just one control action. Can we do this airline recovery itself in a distributed, multi-agent kind of way, right? So that's the reason why we sort of submitted it to AMAS, and that was appreciated there also. So basically, the idea in the second paper was I have like a bunch of flights. They all have these dependencies between each other. Can they sort of somehow exchange messages and come to a consensus as to what would be like a globally optimal way? And because each flight will only talk to others who are affected by it, or neighbors who affect this particular flight, there is a question of scale, right? Scale automatically sort of comes up because you exchange messages only with your neighbors as opposed to your entire airline network, right? So this was like very scalable. Compared in this case, we actually compared it with like a central optimization where you said I have infinite compute time, I have all the data, I have an oracle which gives me perfect performance, and we were able to do much faster than this with like maybe 10-20% less in terms of like the objective that we want to achieve. Okay, so that was the trade-off that we explored in this decision making. So this is a good example where you had a discrete event simulation model of the underlying physical system. It's a transportation system in this case. And we use this agent based approach to sort of come up with decisions. Okay. So let me maybe, in the interest of time, I'll probably just breeze through it, right? So the problem here in this case, the last case study is EV routing, right? So what I mean by this is I have a bunch of customers, and imagine you have like a EV fleet which needs to visit all these customers, and they need to resupply their energy store by either charging or do a battery swap. And in addition, if you have a smart grid, right, so these EVs can actually give energy back to the grid. Okay, so there are like a whole bunch of constraints, not just transportation constraints but also charging constraints, which are new for the EV domain. So this is the way this EV vehicle routing is different from the classical vehicle routing problem. Okay, and the way again we did this was to have like a learning agent, sorry about the typo there, which figures out what is the best way to do the routing in a dynamic manner. So we had a offline plan with which we start, and then the agent iteratively improves on the plan, right? So this work is it got the best paper at CODS COMAD conference, I think in 2023. There was also a follow-up paper in 24 where we did this system of system things, where you have like a joint decision making between the HVAC system of a building and the EVs which are parking in that facility, right? So this is a problem that we encounter at IIT Madras Research Park, right? So we have sort of solved this problem by having like a battery bank to some extent. So we have solar, we have EV chargers, we have the HVAC system. All of these things are like big consumers as well as producers of energy, right? So how do we dynamically tweak all of these things to make a win-win situation for everybody? Okay, so that's the problem that we tried solving. Okay, so some morals of the story so far, right? So I've sort of talked about decision making for physical systems. What are the take-home messages? First point is very simple: aim for scale over accuracy. So we want real-time decisions for real-world systems, right? So which means that I don't really care too much about being provably optimal or theoretically sound, etc. Right? Any heuristic or like an approximate agent kind of like approach, which gives me a reasonable regret with respect to an offline Oracle optimal approach, uh, is good enough. Okay, so that's the first moral of the story. The second one is extensive data collection may not be possible in physical systems, especially brownfield systems. So you need a lot of domain knowledge. You need to have math in terms of like physics-based models, or you need to have discrete event simulations, which can handle the digital twin part of things. And this is what you can use to bootstrap your data collection. Okay. Third point is there is no one size fits all, right? So this is what Krishna was also alluding to. So you need many different models and techniques to solve problems, especially when it is a system of systems, right? If I have an intelligent transportation system, an approach that works for EVs will not work, for example, for the rail network, right? Even though the EV may be feeding passengers to the rail network. If I have like drone taxis, right? Something which takes passengers from the top of IIT Madras Research Park. ePlane is a company which is incubated out of IIT MRP and TCS Research. We work with them closely. So ePlane has like these drone taxis. Now, how do I integrate these drone taxis as part of a multimodal transportation system, right? So these are problems which are interdisciplinary, interdomain, and they require like a lattice of many kind of models and techniques. So last point, again, I want to emphasize this is if you have any hope of deploying your ideas in the real world, I would say you need to work on explanations over anything else, right? Doesn't matter in terms of scale, it doesn't matter in terms of accuracy. Explanations matter a lot. Okay, people must understand why they are suggesting. I mean, why the system is suggesting something that they should implement. Okay, so I want to switch gears slightly, right? Everybody keeps talking about an agentic AI taking over the world, taking over decision making in general, right? What does this mean for physical systems, right? So that's the point I would like to explore for a couple of minutes, and then I will stop for questions. So, like with the classical AI agent, so what is a classical AI agent? You have a particular task and it needs to improve its performance on the task. And how does the agent do that? It does that by some combination of search or machine learning, right? It's some combination of these two things at the heart of it. Of course, there are many variants, many possibilities. Now, in the agentic AI, there are other things which the agent can do. First, it can learn how to decompose a task into subtasks. Okay. And it can call other agents for help. It can also call other tools if necessary for making these decisions. Right. Now, what this means is all of these things are dynamically decided by the agent. Right? If you look at classical AI, the learning algorithm was always fixed. The search algorithm was always fixed. Of course, there will be some parameters and some annealing of the parameters usually, but it is usually decided before the agent is deployed. Here, the agent can dynamically decide what to do, including invoking other agents and tools, right? So the so-called routing, which this agent is capable of doing, is the difference between classical AI agents and the agentic AI agents. Okay. Now, what is it under the hood if I look at it, right? So I have like a system or process. Maybe I have an assistant which I want to use to improve this process. This assistant will have a lot of things behind the hood, under the hood, right? So you have some LLM associated with it. You have a vector database. It has some learning. It has some planning, and most importantly, it has an ability to route a particular prompt or event to other agents and other tools, right? Now, this, in my opinion, this ability to route and call other agents, I think it's a new degree of freedom which was not available in conventional AI so far. Right? With LLMs, there is like this semantic routing which is possible, and there is this ability to sort of use natural language, vision, all of these things to communicate with entities which were usually just programmed. Okay, so this is what is going on under the hood. What does this mean for physical systems, right? So, I mean, if you're a Star Wars fan, you may recognize this, right? I think R2D2 is like the, in my opinion, it is the uh, possible, what is possible, the art of the possible in terms of like agents for physical systems, right? Now, these physical agents, in addition to all the software stuff that you have access to, right, which is basically your cyber world, you have your digital twin, you have your optimization tool, you can have a reinforcement learning also component available. All of these things are possible. In addition, these physical systems will also have capabilities for autonomous decision making on the device itself, right? So this is, I think, the brave new future which is coming. And in fact, I think Google had some releases very recently, right? So they have these vision language models, and then robotics on the device, and so on, right? So a lot of very recent releases are there. Okay, so I believe that the decision making for physical systems of the future will involve a lot of robotics. It will not be, get everything, let's do things in software alone. I think a lot more physical actuation will also be involved. That and the coordination between multiple physical agents or robots is going to be the key for the evolution of physical intelligence. Okay, so I'll probably stop here and react to any questions or comments. Thanks very much for having me here.
Sure, Arun. I think this is very interesting talk, and towards the end, stressing on the aspects of what it means, agents, evaluation of agents for the context of physical, cyber physical systems. I really liked
Correct.
it. I think maybe given a few more minutes of time is left, and I didn't see many questions on the Q&A. Maybe can we take a couple of more questions? I have one is um, again from the perspective of the attendees. I wanted to make it a little bit broader enough. Do you see any opportunities in terms of many different types of AI models? You talked about RL-based solutions, right? Similarly, there are solutions like federated learning kind of solutions. Probably these are all distributed environments. They can have applicability of adapting such techniques. So, can you please elaborate on different opportunities in terms of few other technologies which may have role to play in such settings and limitations?
Sure, sure. See, I think this multi-agent RL, right? I think it's called Marl or Marlow or something, right? So using multiple agents in a coordinated way to solve a cooperative problem, right? That is more or less in a reasonable shape, in my opinion, because there is like a single stakeholder, right? So in an airline, for example, let me go back to this aviation context because it comes across very beautifully there, right? Um, all the aspects of the operations which are under my control. So suppose I am, say, Air India, things which belong to me, the resources, etc. I can manage them in a cooperative setting. Okay, so all of them are my control. I win some here, win lose some there. Net it benefits me. That's going to be my objective. I think what is going to be more challenging is if I have multiple separate stakeholders all competing for the same resource,
Mhm.
right? Now, this kind of stuff usually happens in an airport setting. Suppose the runway is closed for some time, right? Now, all the airlines will be stuck there. Okay, they need to take off and resume their normal operations in the rest of the network. But that access to the runway will now be a contention. it will not be like a shared kind of like a
Yeah.
cooperative way. It's more of a competitive thing. That I think will be the challenge. How do I resolve this multi-agent decision making where there is no centralized stakeholder, right? So this is where I think this agentic AI really can help, right? It almost like it's like a bidding kind of thing, right? So suppose that runway is closed and it is opened and there are only few slots which are available. Will you give the slots to the people who have been most delayed? Or somebody can tell the airport, I will pay you extra, you please let me go because this flight is extremely critical for me, high value passengers are there, and so on. So resolving this in a competitive setting, I think, is the next real challenge. A lot of game theory. I mean, this has been studied from a theoretical perspective for a very long time. I think a lot of theory is there. Realizing it in practice will be the challenge, in my opinion. Yeah.
Sure, Anand. Yeah. Thank you. Thanks a lot. I think given there are no other questions, maybe we can close few minutes early and give back. But thanks a lot for the wonderful presentation and thank
Thank you, Krishna. Thanks, everybody. Thanks to the participants for listening. Thanks a lot.
thank you.
Bye.